In this video, we will look at the basics of establishing identities, or some textbooks call it verifying identities. Again, it will be important for us to remember all of the identities we have learned up to this point. So these, on this slide, are those identities that you should have memorized. So what is an identity? An identity is a statement that the left-hand side of an equation and the right-hand side of an equation are identical for every admissible value of x. So how do we establish or verify an identity? We start with the left-hand side of our identity, whatever that expression would be, and then we use either algebra or a trigonometric identity to rewrite it. And we continue to do that until we have simplified it or rewritten it, manipulated it so that it becomes the right-hand side. So there are usually several steps here. There's no rule on how many steps it needs to take, but all of these steps are just manipulation through algebra and the use of trig identities. So let's take a look at an example. So here we have the left-hand side is cosine squared of beta minus sine squared of beta, and we will use a trigonometric identity to rewrite this. So the goal is to write the left-hand side so that it becomes the right-hand side. So we manipulate this, but always keeping an eye on the right-hand side. So as we look at the right-hand side, you'll notice that there's a sine squared of beta and no cosine squared of beta. So let's use a trig identity to rewrite cosine squared of beta. Cosine squared of beta using a Pythagorean identity can be rewritten as 1 minus sine squared of beta. So at this point, all we've done is rewritten this cosine squared of beta. We now need to subtract sine squared of beta that corresponds to this piece of the left-hand side. Now, we'll use algebra to collect like terms on the right-hand side. So 1 minus, and then we have sine squared of beta minus sine squared of beta. That's minus 2 sine squared of beta. And now you'll see that the right-hand side has been obtained through the use of trigonometric identities and algebraic manipulation. Let's look at another. So we'll start with the left-hand side, cotangent cubed of t over cosecant of t. So let's look at the right-hand side and get some perspective. You'll notice cosecant squared of t minus 1 is present. That feels an awful lot like a Pythagorean identity that we know. 1 plus cotangent squared of, in this case, t equals cosecant squared of t. So if I were to subtract 1 from both sides, we have cosecant squared of t minus 1 is that cotangent squared of t. Well, I don't have cotangent squared of t, I have cotangent cubed of t. So let's separate the cotangent cubed of t. So we get cotangent of t, cotangent squared of t over cosecant of t. Now we will take the cotangent squared of t and reserve it to make cosecant squared of t minus 1. So we have cotangent of t over cosecant of t times cotangent squared of t. So we have cotangent of t over cosecant of t times cosecant squared of t minus 1. Now it comes down to manipulating this fraction so that it is just cosine of t. So we have cotangent of t, and then we can use cosecant of t's reciprocal identity to know that if I divide by cosecant of t, that's the same thing as multiplying by sine of t. And cotangent of t is cosine of t over the sine of t by way of the quotient identity. And now the sine of t cancels. And we have cosine of t times cosecant squared of t minus 1, as desired. So let's look now at the next identity to establish. We have secant of u minus the cosine of u, and we want to transform that. Well, let's use the fact that secant of u is 1 over cosine of u by the reciprocal identity. Now, what we can do is we can get a common denominator and subtract these two fractions. And we will need to multiply by cosine of u over cosine of u to build up the denominator. So we have 1 over cosine of u minus cosine squared of u over cosine of u. And now that we have the same denominator, we can go ahead and subtract the numerators. And it's very important in establishing identities that we don't skip steps, because we're trying to show how we're using algebra and the identities, the trig identities, to establish a new identity. So steps mean everything in these. Now, Pythagorean identity says that the numerator can be rewritten as sine squared of u and now I know that sine squared of u is the same thing as sine of u times the sine of u. So let's split up this fraction. This is the sine of u times the sine of u over cosine of u. If you're having difficulty seeing this, this is the same thing as sine of u over 1 times the sine of u over cosine of u. So we have sine of u, and then sine of u over cosine of u is tangent of u, which is the right-hand side. So this one is a tad bit more complicated, but we don't get intimidated. And the nice thing about identities is there's more than one way to establish most identities. So we'll take a path here, but don't feel like if you didn't want to take this path that you're stuck to what I'm doing here. There is more than one way to do this. So, and that way might be easier. So let's get started. One way to do this is to take our cotangent of theta and rewrite that using the quotient identity. So we have cosine of theta times cosine of theta over sine of theta. And that will be all over 1 minus the sine of theta. Now don't forget the subtraction of 1. That's very easy to leave off in this problem. So now this is equal to, let me simplify that numerator. We have cosine squared of theta over sine of theta over 1 minus sine of theta minus 1. Now, at this point, I want you to notice something. We have cosine squared of theta, and in this denominator, we have 1 minus sine of theta. Now, 1 minus sine of theta is nothing special, but 1 minus sine squared of theta would be. So, can we force that to be a difference of squares? Can we force that to be 1 minus sine squared of theta? But before we do that, let's go ahead and simplify how many fractions we see here. So let's put this over 1. And now, what we can do is whenever we want to simplify a compound fraction, what we can do is we can multiply the numerator and the denominator by the same quantity, the LCD. So let's multiply the numerator by sine of theta and the denominator by sine of theta. And don't forget the minus 1 that we're carrying down. So now this yields for us cosine squared of theta over 1 minus sine of theta times sine of theta minus 1. Now, let's go ahead and take cosine squared of theta. And my initial assumption was that I could multiply this by 1 plus sine of theta and somehow simplify the numerator by canceling. But in fact, what I want to do is I want to take cosine squared of theta and rewrite it so that I see my difference of squares. And then I could cancel that out. So cosine squared of theta is 1 minus sine squared of theta. So as of right now, I can't cancel. But that numerator is now a difference of squares. 1 plus sine of theta, 1 minus sine of theta, all over now 1 minus sine of theta minus 1. And 1 minus sine of theta can cancel. So now we have 1 plus sine theta over sine of theta minus 1. Now I can split that fraction up over a common denominator of sine of theta. So 1 over sine of theta plus sine of theta over sine of theta minus 1. So what happened? Let's go backwards. I have two fractions here that have the same denominator of sine of theta. I can add the numerators, 1 plus sine of theta. And this subtraction of 1 just coincides with the subtraction of 1 that we had. So I really just split up the numerators over a common denominator. You cannot do this if it's a numerator that you're trying to keep the same and a denominator split up. You can only split up a numerator, not a denominator. So because I have two terms in the numerator, I can go ahead and split that up. So now, 1 over sine of theta is cosecant of theta. Sine of theta over sine of theta is 1. Subtract 1, and that yields cosecant of theta as desired. So let's look at our next example. We have cotangent of alpha over cosecant of alpha plus 1. Keep in mind here that the alpha is the only thing that we're taking cosecant of in that denominator. So you could put alpha in parentheses if you wanted to highlight that. So this equals. Now what we're going to do in this problem is let's use the trick of forcing the denominator to be a difference of squares. So we're going to multiply by cosecant of alpha minus 1. Now the numerator, I'm not going to multiply out. But the denominator is cosecant squared of alpha minus 1. Now you'll remember your Pythagorean identity to help that denominator simplify. Cosecant squared of alpha, if you remember the original Pythagorean identity, is 1 plus cotangent squared of alpha equals cosecant squared of alpha, which means that cotangent squared of alpha equals cosecant squared of alpha minus 1. So that helps us transform the denominator to be cotangent squared of alpha. Now, that cotangent of alpha will cancel with 1 of our cotangent of alpha in the denominator. And so we have now cosecant of alpha minus 1 over cotangent of alpha, which is the right-hand side.